Alright, in this video we are going to introduce a new topic, momentum. Now for the most part, a lot of people can describe what momentum is. It's kind of an inertia really, but it quantifies it. So we're going to state that momentum p, which is a vector, is simply equal to mass times the velocity. The units for these would come out in kilograms, meters per second. No fancy shortcut unit, that's it. So by itself, momentum really isn't much. There's nothing exciting about it. It's just P equals mv. What gets more interesting is when we start asking questions like, well, what causes not just causes momentum, but what causes a change in momentum? Okay, that's where things get a little more interesting. Now, it should be kind of obvious, but well, if something's moving with a speed and it has mass and I want to change that speed, what should I do? Well, it's easy. I need to apply a force. A force is what changes the momentum of an object. So let's go through a small example and kind of see how that works. So let's start with a simple idea. We've got a box or some object of mass m, and it's moving with some initial velocity, v0, and we push with a force or apply a force, and the key here is we apply a force over some time interval. Okay. Now as a result, we know because of Newton's second law, and first law for that matter, we apply a force and that's going to change the velocity. So assuming no friction and no other resistive forces, let's just say one force, we change the velocity. So the final velocity is definitely not going to be the same as the initial. Okay. So m hasn't changed, but v has. This obviously means that the force we applied changed the momentum of the object. Okay? So let's kind of work through a small calculation. Again, we're just kind of dealing with variables here, but we're going to come up with a rather interesting result. Okay, so let's start with what we know. You have a force which is equal to mass times acceleration. This is Newton's second law. But we can manipulate the acceleration a little bit. We know that acceleration is simply the time derivative of velocity. Now, a calculus concept here. Mass is constant, so it doesn't really matter whether it's outside the derivative or inside the derivative. So let me just put it inside the derivative, not breaking any mathematical laws here. But you'll notice that that term in parentheses is what we just defined as momentum. So it turns out that a force is actually the time derivative of momentum. Okay? Say that again. Force is the rate of change of an object's momentum. Okay? In fact, this is actually the definition for Newton's second law. This was the formal definition that Newton himself actually wrote about in his Principia, which of course is the start of all physics, is that a force is simply described as the rate of change of an object's momentum. Now when a force causes a change in momentum, it has a special name. So a force that changes the momentum of an object is called impulse. So let's look at how we actually can calculate an impulse. So we'll start basic with Newton's second law. Force is the time derivative of momentum. Now we're going to basically solve this out using calculus. So we did this with air resistance, right? We separate the variables by multiplying dt to both sides, so it cancels on the right. On the left side, we've got force times the time derivative is equal to the derivative of momentum. So to solve this, we're going to take antiderivatives of both sides. On the right side, well, The antiderivative of momentum will simply just be a change in momentum, final minus initial. So we've identified that and defined that before. That's change in momentum. What about the left side? So we have force times the time derivative, and it's an integral of all this. Well, that integral is what we call the impulse. And it has its own special letter. It's a capital J. So J is impulse, which is the integral of force dt. Now, this only makes sense, and we only use this if force is a function of time. But that's not always the case. Sometimes we get a little more easier with that. We don't need to go that technical. So if F is constant, if the force is constant, or if in a real applicable problem we just want to look at the average force, then the impulse is actually the force, constant or average, times whatever the change in time is. Now when we combine all this together, impulse is the integral of force over time, which is also equal to the change in momentum. We refer to this as the impulse momentum theorem. Now we'll use this quite a lot through the unit to start off with because it's kind of a nice way to combine the ideas of forces as well as kinematics. So let's go through an example and kind of show how this works. Okay, so for the first example, we're going to do this graphically. Okay, so plain and simply, find the change in momentum for an object that has a force exerted on it as given by the following graph. Okay, so we'll make a quick graph here. It's a force versus time, force on the y-axis, time on the x-axis graph. Now typically for a momentum impulse graph, it tends to be just a spike in force. Because when you apply an impulse, it's just a quick push or pull on an object, and it's usually done over a quick time interval, but we're going to make the numbers kind of large here so it's easier for us to see it in our calculations. So this is going to be between 4 and 11 seconds, and we'll say the force peaks at around 12 newtons. Now the impulse momentum theorem tells us that the integral of force over time is equal to the change in momentum. But remember from calculus that an integral is simply the area under a force time curve based on these variables. So what we want to do is find all this area. This area represents our change in momentum, and because of its equivalency in the impulse momentum theorem, this area is also your impulse. So to quickly calculate the area, half base times the height. The base is the difference between 11 to 4. The height is 12. So we will crunch all of this out, and we'll come up with 42 kilogram meters per second. Okay, so we'll do a little baseball example here. So a baseball, we'll say, is thrown towards a batter, and it's moving at 42 meters per second. Okay, the batter will then swing the bat and contacts the ball for 3 milliseconds. This causes the ball to fly away at 68 meters per second. So how much force did the bat exert on the ball? Now we're going to assume the force is constant. Of course, it's not a constant force, but we're going to make this kind of easier on ourselves. So we'll look at just the average overall force acted on the ball, which if we use impulse momentum theorem, force times time is your change in momentum. So we're going to solve this for force. So we're going to do final momentum minus the initial momentum divided by time. So that's mvf minus mvi over change in t. Now we'll factor out the m at the top, and the mass of a baseball is about 0.145 kilograms, and final velocity was 68, initial velocity was 42, and you'll notice that on the bottom, the time it was in milliseconds, so we have to convert that to seconds, so that's times 10 to the negative 3. So when we crunch all of this out, we will get a force of 1,260 newtons towards the outfield. Keep in mind, force is a vector, so it has direction, so specifying that it's towards the outfield. So let's try another example. In this one, we'll employ some calculus concepts. Okay, so a 5 kilogram object has a force exerted on it as a function of time. And we'll define that function as f of t is equal to 2t plus 3. Of course, this whole expression is a force, so it should be in newtons. So the question then is, what is the object's velocity at t equals 3 seconds? If it was moving at 16 meters per second at t equals 1 second. Okay, so the first thing that you need to pull out of this question is that notice that the force is a function of time, and the word function is very important here because it's telling us that this is not a constant force, nor is it an average force, which means we have to use integral calculus and the impulse momentum theorem to solve the problem. So we write out by doing our integral from 1 second to 3 seconds of our force function 2t plus 3 over time. And the change in momentum is your mass times final velocity minus the mass times initial velocity. So to take the antiderivative, you should know fairly well how to do this. Add 1 to the exponent, divide by that number. And for the 3, since there wasn't a t, we're going to throw a t on there. And don't forget, we have to evaluate it from 1 to 3. So remember, to evaluate the integral, we start by plugging in the upper limit to that function, and then we subtract when we plug in the lower limit. Right, so when we crunch all of it out, 3 squared plus 3 times 3, well, that's 9 plus 9, so that's 18, minus 1 plus 3, which is 4, and that's going to give us a change in momentum. So let's finish crunching this out. So 18 minus 4, that's 14 kilogram meters per second. And on the right side, the mass of the object was 5 kilograms times the final velocity minus 5 kilograms times the initial velocity, which was 16 meters per second. Okay, so we're going to crunch through some algebra here. 5 kilograms VF minus 5 times 16, which will be 80 kilogram meters per second. Bring the 80 to the other side. So we have 94 kilogram meters per second is equal to 5 kilograms times the final velocity. So our final velocity will be 94 divided by 5, which is right around 19 meters per second.